Right now, as you breathe, you are racing through space at over 1 million miles per hour. The Milky Way is being dragged towards something we cannot see, a hidden mass with the gravity of 100,000 galaxies, sitting behind a wall of cosmic dust. Today, we cross a void darker than night, chase a stream called dark flow, peek behind the zone of avoidance, and stand at the edge of a structure so vast it bends the fate of our galaxy. If cosmic mysteries thrill you, hit that subscribe button and stay close. Prepare yourselves. We begin. You are standing still right now, or so it feels. Your feet press the floor, the room holds steady, gravity keeps you anchored. Reality has other plans. In 1 second, you traveled around 300 miles around Earth's spinning axis. In that same second, Earth shoved you 18 miles further around the Sunday. The Sun pulled you another 130 miles around the heart of the Milky Way, and the entire Milky Way carried you over 370 miles towards something nobody can see. Add it up, and you are flying through space at roughly 1.5 million miles per hour, faster than any rocket, faster than any bullet humanity has ever fired. And the strangest part is that none of these speeds line up neatly. Each one points in a different direction. For most of human history, we believed Earth sat at the center of everything. Then we learned the Sun was the center, then the galaxy. Each time, the universe got bigger, and our place in it got smaller. By the 1970s, astronomers thought they finally had the picture sorted out. The galaxies were drifting apart from the Big Bang, like raisins in a rising loaf of bread. Then the numbers stopped behaving. A team of 7 astronomers, later nicknamed the 7 Samurai, started measuring how nearby galaxies were moving. They expected a clean pattern. Galaxies should be drifting outward, smoothly, in every direction. Instead, the data showed something disturbing. Hundreds of galaxies, including ours, were not just drifting, they were rushing, all of them sliding sideways in the same direction, like leaves caught in an invisible river. Whatever was pulling them was massive. Whatever was pulling them was hidden, and whatever was pulling them did not appear on any star map we had. Picture standing on a frozen lake. The wind blows your hair, but your feet stay put. Then you glance down and see the entire surface of the lake is sliding. Not melting, not cracking, just slowly moving towards something distant. You cannot see what is dragging the ice. You only know your boots are going wherever it goes. That is what astronomers found in our cosmic neighborhood. The Milky Way, the Andromeda Galaxy, and tens of thousands of others, all caught in a current, pulled by something staggering, pulled by something so dense that its gravity reaches across 250 million light-years to grab us by the collar. The numbers were almost too embarrassing to publish. The team checked the data again. Then they ran simulations. Then they argued some more. Some scientists refused to believe it. The math felt wrong. A monster gravity, well, sitting in our backyard, hidden from every telescope, sounded like a bad science fiction plot. But the math kept winning. By 1987, the team gave the thing a name. They called it the Great Attractor. Not because they understood it. They named it because they had to call it something, and the truth was simple. Something out there was attracting us, greatly. The deeper they dug, the worse the picture got, because behind the first mystery sat a second one, a region of sky no telescope on Earth had ever been able to see clearly, a wall of cosmic dust standing between us and the answer. Look up at the night sky on a clear evening, away from city lights, and you will see a pale river of stars stretching from one horizon to the other. That milky band is our own galaxy, seen edge-on from inside. The Milky Way looks beautiful from the outside. From the inside, it is a problem. That bright band of stars hides about 1/5 of the entire sky from us. Astronomers call this hidden zone the Zone of Avoidance. The name fits. For over a century, telescopes have avoided it, because trying to look through it is like trying to read a billboard through fog at midnight. Imagine living inside a glowing snow globe. The glass is thick, the snow swirls. Outside the globe, mountains and oceans and entire cities exist, but you cannot see any of it because the light from the snow drowns everything out. That is what astronomers face every time they aim a regular telescope toward the heart of our galaxy. The dust, the gas, and the sheer brightness of billions of nearby stars block the view of the universe beyond. For decades, the Zone of Avoidance was a frustration, a blank patch on the cosmic map, useful only as something to work around. Then, the Seven Samurai dropped their bombshell. Whatever was pulling our galaxy across space was sitting almost exactly behind that hidden zone. The biggest gravitational anomaly ever detected was hiding in the one part of the sky we could not see. Astronomers reacted the way you would expect, with a mix of excitement and panic. Excitement because something huge was clearly out there. Panic because the universe seemed to be hiding it on purpose. The odds of an object that powerful sitting behind the only blind spot in our sky felt absurd. Some researchers wondered whether the dust itself was somehow part of the puzzle. Optical telescopes were useless here. They saw stars and dust, nothing more. The team needed a different kind of vision. Radio waves became the first key. Radio light travels straight through dust like sunlight through window glass. Then came infrared, which sees heat instead of color. Then X-rays, which slice through gas like a blade. Each kind of light revealed something the others missed. Stack them together, and the dusty curtain started to thin. What the new telescope saw stopped scientists cold. Behind that curtain were galaxies, lots of galaxies, hundreds of them, then thousands, packed together in a region nobody had mapped before. Whole clusters of stars hidden behind our own galaxy, never recorded in any old chart. The Parkes radio telescope in Australia spent years scanning the zone and reported that more than half of the obscured radio sources turned out to be brand new galaxies nobody had ever seen. Since the year 2016 alone, the number of known structures in this region has jumped by about 50%. Imagine pulling back a curtain in your house and finding an extra living room you never knew existed. Now imagine doing that and discovering the whole room is rushing towards something even bigger in the next house over. That is what astronomers found. The hidden galaxies were not random. They were arranged into walls and clusters, all leaning toward one specific spot on the sky, a single direction in the constellation Centaurus. Whatever was pulling, it had an address, and we were finally close enough to start knocking. Here is something that should disturb you. Right now, the Milky Way is falling, not orbiting, not drifting, falling, toward a destination it never agreed to go to. Most people picture our galaxy as a peaceful pinwheel, spinning in place like a top on a table. The reality is rougher. Our galaxy is moving through the universe at around 1.5 million miles per hour relative to the leftover light from the Big Bang. That leftover glow, called the cosmic microwave background, fills all of space evenly in every direction. If we were sitting still, the glow would look the same on all sides. It does not. When astronomers measure that ancient light very carefully, one half of the sky looks slightly hotter and slightly brighter. The opposite half looks slightly cooler and slightly dimmer. This is a clue. The same effect happens when you drive a car into rain. The drops on your windshield hit harder than the drops on your back window. We are driving into something. The hot side of the sky is the direction we are heading. That direction points straight at the Centaurus and Hydra constellations, straight at the Great Attractor. The cosmic microwave background is famously flat and even. It is described as the most uniform thing ever measured. So when something punches a noticeable bias into it, that something has to be powerful. To pull a galaxy weighing 1 trillion suns at over 1 million miles per hour, you need gravity on a scale that breaks normal thinking. Picture a marble on a stretched bedsheet. The marble sits still. Now drop a bowling ball on the sheet a few feet away. The bedsheet sags. The marble rolls toward the bowling ball, picking up speed. That is gravity in 2 dimensions. Now imagine the bedsheet is the entire universe. The marble is our galaxy, with all its stars and planets and oceans and life. And somewhere out there, a bowling ball is denting space itself. The sun rides along for the trip. So do all the planets. So does Earth. So do you. Every breath you take, you are also accelerating slightly toward a point in the constellation Centaurus. Astronomers call this kind of motion peculiar velocity. The word peculiar here does not mean strange. It means specific, personal. A peculiar velocity is the speed of a galaxy on top of the regular expansion of the universe. It is the part of the motion that has nothing to do with the Big Bang and everything to do with local gravity. Our galaxy's peculiar velocity is enormous, around 1.3 million miles per hour, all aimed at one direction. To grasp what that pull requires, imagine catching a planet with a fishing line. Now imagine catching 100,000 galaxies with one. The Great Attractor has an estimated mass on the order of 10,000 trillion suns. That is the weight of tens of thousands of galaxies condensed into a region of space. Whatever it is, it has the gravitational grip to drag entire star systems off course, like cars on a tow truck. And the chilling part is that it has been doing this for billions of years, long before Earth had oceans, long before the first cell ever divided. The Milky Way has been falling toward this thing for nearly the entire age of the cosmos, which raises the question every astronomer wants answered. How long before we get there? In the early 1980s, 7 astronomers set out to do something that sounded boring on paper. They wanted to measure how galaxies move. Distance, direction, speed. That was it. What they found made them famous, and the data they collected almost broke modern cosmology. The team called themselves a research group. The press called them the Seven Samurai. Their leader was Alan Dressler at the Carnegie Institution. They surveyed around 400 elliptical galaxies in our cosmic neighborhood, painstakingly clocking each one. The plan was simple. Subtract the universe's expansion from each galaxy's motion. Whatever was left over would tell them about local gravity. The plan worked. The result did not match anything they had expected. Every single galaxy in their sample, including the Milky Way, was sliding toward the same patch of sky. Not random drift, not statistical noise. A coordinated motion of hundreds of galaxies, all leaning in one direction, all moving at hundreds of kilometers per second on top of the normal expansion. They had stumbled onto something gigantic. To understand how strange this was, picture standing in a crowd at a busy train station. Some people walk left, some walk right, some stand still. That is what the universe was supposed to look like on large scales. Now imagine you watch the same crowd and notice every single person is also drifting 2 steps to the north every minute, no matter what they are doing. The drift is gentle, but universal. Something is pulling the floor. The number the 7 Samurai measured for our peculiar velocity was around 600 kilometers per second. That is roughly 1,300,000 miles per hour. For a single galaxy, fine. For an entire cluster of hundreds of galaxies all moving the same way, it was shocking. Galaxies that big should have been gravitationally independent. They should have wandered. Instead, they were marching in formation. The team published their findings in 1987. The reaction was loud. Some scientists thought the measurements were wrong. Others suspected calibration errors. A few quietly hoped the entire conclusion would fall apart in a few years, because it would be much simpler if it did. It did not fall apart. Other surveys repeated the work with newer telescopes and bigger samples. The result held. The flow was real. Galaxies in our part of the universe really were streaming toward an unseen point. Dressler later joked that the team did not set out to find anything weird. They had been hunting for a clean measurement of cosmic expansion. They got handed a mystery instead. He compared it to going fishing for trout and pulling up a creature you cannot identify. Then came the harder question. What was big enough to do this? A single galaxy could not pull this much. A single cluster could not. To explain the streaming, you needed something with the mass of tens of thousands of galaxies, all packed into a region only a couple of 100 million light years away. Nothing on any star map matched. This was when somebody, finally, gave the invisible monster a name, the Great Attractor, a label for ignorance, dressed up to sound serious. The deeper astronomers stared at that direction in the sky, the more unsettling things they started to see. Because the gravity well was not just deep, it was crowded, and the closer they looked, the more layers it had. Before chasing the attractor any further, we need a map. Without one, the scale of what is happening makes no sense. Earth is small. Our home planet measures about 8,000 miles across. Around it spin a moon and a thin layer of atmosphere, a tiny bubble. Around Earth sits the solar system. 8 planets, dozens of moons, millions of asteroids, all bound to the Sunday light from the sun takes about 8 minutes to reach you. Out at the edge, where the sun's grip finally fades, light takes around a year to travel. Already, the numbers are becoming hard to picture. Around the solar system sits the Milky Way, a flat spiral of about 400 billion stars, glued together by gravity and an unseen scaffold of dark matter. To cross our galaxy at the speed of light would take 100,000 years. Light is the fastest thing in the universe, and it cannot make the trip in a single human lifetime. Around the Milky Way is the local group, a cluster of around 80 galaxies, including Andromeda. The group spans about 10 million light-years. Now things start to break the brain. The local group sits at the edge of a much larger structure called the Virgo cluster, which is the heart of the Virgo supercluster. For decades, astronomers thought this was where our cosmic address ended. Then, in 2014, Brent Tully and his team redrew the map using a new technique that traced not just where galaxies are, but how they move. They realized the Virgo supercluster is not the top of the structure. It is just a province of something far bigger. They called this larger structure Laniakea. The name comes from Hawaiian and means immeasurable heaven. Laniakea contains about 100,000 galaxies, sprawled across 500 million light-years. The Milky Way lives near the outer edge. Picture a watershed on Earth. Rain that falls on one side of a mountain ridge runs into the Atlantic. Rain on the other side runs into the Pacific. The mountain decides where the water goes. Astronomers do something similar with galaxies, but instead of rain, they trace the motion of each galaxy. If a galaxy is being pulled toward a certain region by gravity, it belongs to that region's basin. Laniakea is one such basin. Every galaxy inside it, including ours, is flowing toward a single low point in the cosmic terrain. That low point is the Great Attractor, the deepest part of the basin. The drain? We do not orbit it. Our galaxy does not loop around the Great Attractor the way Earth loops around the Sunday. We just fall toward it, steady, continuous, slow on a human scale, terrifying on a cosmic one. Laniakea is 250 times bigger than the old Virgo supercluster estimate. Discovering it was like spending your whole life thinking you lived in a small town, then learning your town is one neighborhood of a megacity nobody had bothered to map. That same map showed something else, something the older astronomers had missed. Laniakea has a clear edge. Beyond that edge, galaxies stop falling toward our basin and start falling somewhere else. Other basins, other attractors, and one of those basins, sitting just beyond ours, turned out to be even larger, pulling not just our galaxy, but our entire supercluster as well. If the Great Attractor has an address, the Norma cluster is the front door, sitting around 220 million light-years from Earth. In the constellation Norma, this cluster is the most massive single object found in the obscured zone behind our galaxy. Its formal catalog name is Abel 3627. Astronomers use that name in papers. Everywhere else, it is just Norma. Norma is a galaxy cluster on a serious scale. Hundreds of galaxies are packed into a roughly spherical region. Many of them are giant ellipticals, the kind of galaxy that forms when smaller spirals smash together over billions of years. Cluster cores like this are graveyards of cosmic mergers. Every galaxy you see there has eaten others. At the heart of Norma sits a giant elliptical galaxy known as ESO 137006. It has a supermassive black hole feeding on hot gas. 2 enormous radio jets shoot out from its center, stretching for millions of light years. The jets blast through the cluster's atmosphere of superheated plasma, leaving glowing trails visible to X-ray telescopes. If you could stand near Norma and feel its gravity, you would not get far. The mass packed into this cluster runs into the trillions of suns. Galaxies here move at speeds of more than 3,000 kilometers per second, dancing around one another in a slow, violent ballet. Anything dropped into the cluster from the outside would be flung into wild orbits, stripped of its outer stars, eventually torn apart. But Norma alone, big as it is not quite massive enough to explain everything we see. A cluster like this could pull a few thousand galaxies. The Great Attractor pulls 100,000. The math leaves a gap. For a while, this was a serious problem. The Norma cluster was clearly there, clearly massive, clearly important. It explained a lot of the local flow, but not all of it. Something larger had to be lurking behind it. Picture standing on a beach at dusk. Far out at sea, you see a tall ship sailing toward shore. You can make out its sails, count its masts, even see the figures on deck. Then a wave breaks differently. The ship suddenly tilts. You realize you have been watching the small mast of a much larger ship behind it, hidden by glare. The ship you thought was sailing alone is dwarfed by something monstrous behind it. That is roughly what the Norma cluster turned out to be. A real, important, massive cluster sitting in the foreground of something even bigger. X-ray surveys, especially the Caesar project, have helped peel back the dust around Norma. The Chandra and XMM Newton telescopes mapped its hot gas, traced its galaxies, and clocked its motion. The results were clear. Norma is a real attractor. It pulls. It holds the local flow together. But part of the flow keeps going, past Norma, through Norma. Even after subtracting Norma's gravitational influence, our galaxy is still being tugged by something else further out. That extra tug pointed deeper into the obscured zone, past the dust, past the wall of stars, past the Norma cluster itself, into a region of sky where the cosmic web suddenly gets crowded. A region containing not one cluster, but dozens of them, all packed together, all gravitationally linked. That region had a name long before anyone connected it to the attractor. It is called the Shapley concentration, and it is the next layer of the puzzle. Long before the Great Attractor was named, an American astronomer noticed something weird in a corner of the southern sky. Harlow Shapley spent the 1930s studying galaxies through some of the best telescopes of the era. While scanning the constellation Centaurus, he kept finding clumps of galaxies bunched far closer together than they had any right to be. Thousands of galaxies, packed into a single region. He called it a cloud, a galaxy cloud. The name was modest. The thing was not. Decades later, that cloud got a new name, the Shapley concentration, or, as some astronomers prefer, the Shapley supercluster. It sits about 650 million light-years from Earth, far behind the Norma cluster, far behind the Great Attractor itself. Yet despite that distance, its gravity reaches out and grabs us. Inside Shapley, the densities are staggering. Around 24 rich galaxy clusters cluster around a central spine, tens of thousands of galaxies. Some estimates put the total mass at well over 10,000 trillion suns. For comparison, our entire local group, with all 80 galaxies, including Andromeda and the Milky Way, weighs about 3 trillion suns. Shapley is over 3,000 times heavier than our home cluster, maybe more. It is the largest known concentration of matter in the local universe. Picture cities on a map at night. Most of the lights are scattered, with dim suburbs and wide-open countryside. Then, in one spot, a megacity glows, so brightly, the rest of the map looks empty. That is what Shapley looks like in galaxy maps. A bright knot of light surrounded by a thinner cosmic web. Now, the punchline. When astronomers add up all the gravity in our local neighborhood and try to explain why our galaxy is moving the way it does, the Norma cluster and the Great Attractor account for only part of the pull. The rest comes from much further away. It comes from Shapley. Roughly 44% of the Milky Way's peculiar velocity is now believed to be caused by the Shapley concentration's gravitational tug, even though it sits more than twice as far away as the Great Attractor. The Great Attractor is the big, nearby thing. Shapley is the much bigger, distant thing. Together, they form a chain of masses, pulling us deeper and deeper. This is why some astronomers started calling Shapley the real attractor, or the Shapley attractor. The original Great Attractor turned out to be a stop along the way. Recent analyses have pushed this idea further. In 2025, a new survey called Cosmic Flows 4 mapped galaxy motions out to over 400 million light-years and found that the cosmic flow lines reach all the way to Shapley before fading. Some researchers now suspect the entire Laniakea supercluster, our own home, might be just a smaller branch flowing into Shapley's gravity well. That would mean our cosmic address has another line, not just Earth, Solar System, Milky Way, Local Group, Laniakea, add Shapley Basin too. Or maybe replace Laniakea with Shapley. The map is still being argued over. In real time, in journals, what is not in dispute is the destination. Whatever name we give the structure, our galaxy is heading there. And the road has more bumps than we knew. Imagine you are blindfolded. Someone places a heavy object in your hand and asks how heavy it is. Hard, but possible. Now imagine they tell you not to touch it, just to guess by watching how nearby pebbles fall toward it. Harder. Now imagine the object is invisible, the pebbles are galaxies, and the falling takes 10 million years to measure. Welcome to the job of weighing the Great Attractor. The basic trick astronomers use is simple to state and brutal to execute. Light from distant galaxies gets stretched as the universe expands. The longer the light has been traveling, the more stretched it gets. This stretch is called redshift. The bigger the redshift, the further away the galaxy is, and roughly the faster it is moving away. That is the universe's expansion speaking. But on top of that smooth flow, every galaxy has its own peculiar wiggle. A galaxy near a big cluster might be falling toward the cluster, adding extra speed. A galaxy at the edge of a void might be drifting away from emptiness, shaving speed off. If you can measure the true distance to a galaxy and compare it to its redshift, the difference reveals its peculiar motion. Multiply that across thousands of galaxies, and you can build a map of where everything is being pulled. The catch is that measuring true distance is hard. Most of our universe is so far away that telescopes show only smudges. To get distance, independent of redshift, astronomers use objects whose real brightness they already know. Burst like exploding stars, specific kinds of pulsing stars, patterns in spiral galaxy rotation. Each of these acts like a cosmic ruler. The technique used most often for the Great Attractor is called the Tully-Fisher relation. The faster a spiral galaxy spins, the brighter it really is. Compare its true brightness to its apparent brightness, and you get its distance. Combine that with redshift, and out pops the peculiar velocity. The Seven Samurai, in the 1980s, used a similar technique for elliptical galaxies. Modern surveys, like Cosmic Flows 4, have done it for more than 50,000 galaxies. The dataset is massive. Picture taking a picture of a flowing river using a long exposure. Each leaf on the water leaves a tiny streak. With enough leaves and enough streaks, you can map the entire current, even under bridges where you cannot see directly. Galaxies are the leaves. Their peculiar velocities are the streaks. The result is a three-dimensional map of the cosmic current. When astronomers ran the math, the streaks pointed straight at Centaurus and Hydra, just like the Seven Samurai had said, but with much more detail. The map even revealed the depth of the gravitational well. From the way galaxies fall toward it, scientists calculated a mass on the order of 10 quadrillion suns. That number is awkward for the standard model of cosmology. Some surveys, especially X-ray ones, found that the actual visible mass of the Norma cluster falls short, about 1/10 of what the original mass estimate suggested. The rest of the pull seems to come from further out from Shapley, and from yet more distant structures. This is where the measurements get exciting and a little frightening. Every time astronomers extend the map, the pulling region keeps growing. The gravity well does not have a clean bottom. It just keeps going deeper. Some scientists now wonder if our entire view of cosmic flow is missing a piece, far beyond the edge of the visible universe, a piece that should not be there at all. In 2008, an astronomer named Alexander Kashlinsky at NASA's Goddard Space Flight Center was studying clusters of galaxies, big ones, hundreds of them, spread across the sky. He was using a clever technique. When light from the cosmic microwave background passes through a hot galaxy cluster, it gets a tiny push of extra energy from the hot gas. This push leaves a faint fingerprint on the background light. By measuring the fingerprints from many clusters, you can read off how the clusters themselves are moving relative to the rest of the universe. The expectation was simple. Clusters near us should show motion related to nearby gravity wells. The Great Attractor, Shapley, other local structures, clusters far out, hundreds of millions of light years away, should be moving randomly, since they would be too far from any nearby attractor to feel its tug strongly. Kashlinsky and his team got the opposite result. The faraway clusters were not random, they were all moving in the same direction, a direction roughly aligned with the same patch of sky we have been talking about near Centaurus. The motion was steady, smooth, and present at a depth where it should not have been there at all. Kashlinsky called it dark flow. The name was deliberate. Dark, because the cause was invisible. Flow, because galaxies and clusters were sliding together. Putting the two words together created instant headlines. Some interpretations of dark flow suggested its source might lie outside our observable universe. Pieces of cosmos so far away we will never see them, gravitationally tugging on what we can see. This is a wild claim. The observable universe is the bubble of space, whose light has had time to reach us since the Big Bang. Anything beyond that bubble is, by definition, unreachable, unobservable. We cannot point a telescope at it. We cannot ever shake hands with it. Yet, dark flow seemed to suggest something beyond that frontier was tugging on our side of the curtain. Picture standing on the bank of a wide river. The water flows from upstream to downstream. Now imagine you walk 100 miles downstream, expecting the current to die out. Instead, the river just keeps going. You walk another 100 miles, still flowing. You walk to the very edge of the country. The river crosses the border and keeps going into a country you cannot enter. You will never see the source, but the water keeps coming. That was dark flow. The findings sparked a storm. Other teams jumped in to verify. Some confirmed the basic signal. Others, using newer satellite data from Planck, said the effect was much weaker than reported. The argument is still alive. As of recent years, dark flow remains a tentative finding, not a confirmed fact. What is real, beyond doubt, is that motion at large scales does not match standard predictions perfectly. Cosmic Flows 4 found an unexpected 0.11% tension with the standard cosmological model in 2025. Tiny number, massive implication. Either our uncertainty is underestimated or new physics is involved. Either way, the Great Attractor sits in the middle of this storm. It is the closest piece of an unsolved puzzle that may stretch beyond the universe we know. If something out there is reaching across the edge of cosmic time to nudge us, the Great Attractor is the visible end of that string, and the string keeps going. We turn next to a region scientists found while trying to look the other way. It is just as strange. For decades, astronomers framed the Great Attractor story as a pure pull, galaxies sliding toward a heavy region, standard gravity, just on a huge scale. In 2017, a team led by Yehuda Hoffman published a paper that turned the picture inside out. Galaxies near us were not only being pulled forward, they were also being pushed from behind. The pusher had no obvious source. Behind us, in a direction opposite the Great Attractor, the sky looked emptier than expected. Not just a little empty, profoundly empty. A vast region with far fewer galaxies than it should have. The team called it the dipole repeller. The name comes from the way our motion looks in the cosmic microwave background. One side of the sky is hotter, in the direction we are moving. The other side is colder, in the direction we are leaving. That hot-cold pair is called a dipole. It used to be assumed the dipole was caused entirely by something pulling. Hoffman's team showed half of it was caused by something pushing. A void cannot push, not literally. Empty space has no hands. What it can do is fail to pull. When a region of space contains less mass than the cosmic average, gravity from surrounding galaxies wins out. The galaxies on the edge of the void get pulled toward those other regions. From inside the void's frame of reference, it looks like the void is shoving them away. Picture a beach with two sandcastles. One on your left is huge. One on your right is missing entirely. Even though the missing castle has no sand, you feel the left one pulling sand toward it. From the empty spot's perspective, sand is leaving. That is what the dipole repeller is doing on a cosmic scale. Not pushing, but failing to hold on. The repeller's signature is unmistakable in the velocity data. About half of the Milky Way's 600 km/s motion comes from being pushed by the void behind us. The other half comes from being pulled by the Shapley concentration ahead. Push from one side, pull from the other. Together they explain almost all of our galaxy's wandering. What makes the repeller spooky is its size. Estimates put it at about 500 million light-years across. A single emptiness, large enough to hold thousands of galaxies, missing them all. Astronomers had no idea voids that big could be so empty. Standard models of the universe predict a certain distribution of voids and walls. The dipole repeller, if its current estimate is right, is bigger and emptier than the textbooks expect. Some researchers now suspect the universe has a lot more big voids than we thought. The Bootes void, the local void, the cold spot repeller. Each one, like the dipole repeller, may be quietly nudging galaxies away. Together, they could be reshaping cosmic flow on scales we have barely begun to map. Standing inside our galaxy, you cannot feel the void. You cannot feel the pull either. The forces are too gentle in the moment, but sum them across hundreds of millions of years, and they steer continents of stars. Push behind, pull ahead. The Milky Way is sandwiched between them, riding the gradient like a leaf on a stream. What lies in that stream just past Norma is not a single attractor. It is a chain. When astronomers cleaned up the dust around the Great Attractor, they expected to find a single big cluster. They found a wall. The Norma Wall, sometimes called the Great Attractor Wall, stretches across hundreds of millions of light-years. It is a long ridge of galaxies, packed into a sheet, running across the sky behind our own galactic plane. Inside this wall sit several rich clusters: the Norma Cluster, Pavo, Centaurus Crux, plus a fairly recent discovery called CIZA J1324-7, a cluster found by an X-ray survey of the dust zone. A wall, in cosmology, is not a barrier. It is a sheet of galaxies separating cosmic voids. The cosmic web is not a uniform paste. Galaxies clump along filaments and walls. In between sit huge, mostly empty regions. The Norma Wall is one of the densest walls in our local universe, maybe the densest within a few 100 million light-years. Picture a city skyline at night, but stretched into a strip 3,000 miles long. You are flying over it. Below you, lights cluster into towers and avenues. Outside the strip, the land goes dark. That is what the Norma Wall looks like to astronomers. A bright strip of galactic cities, surrounded by darkness on either side. The wall plays a crucial role in the Great Attractor story. When astronomers search for the source of our galaxy's pull, they find that the Norma Wall holds a large fraction of the answer. Not just the Norma Cluster, but the entire ridge of structure connected to it. Mass spread out along a line, summing up into a gravitational anchor. Studies in recent years have shown the wall reaches even further than first thought. It continues into the constellations Centaurus and Vela. Some astronomers now suspect the Norma Wall and the Vela supercluster are part of a single giant feature. The Vela supercluster, discovered in 2016, is another huge mass concentration also hiding behind the Zone of Avoidance. It sits about 800 million light-years away and may add more pull to our local flow. If true, then the Great Attractor is not a point. It is more like a cliff, a long rising shelf of mass. As our galaxy slides toward it, we are moving toward a structure that gets denser the deeper we look. There is a reason astronomers use the metaphor of a watershed for these regions. Imagine standing at the foot of a mountain range. From far away, the range looks like a single peak. As you walk closer, you realize there are 5 peaks. As you walk closer still, you see those peaks are connected by ridges, walls, saddles. The range is bigger and more complex than it first appeared. That is what has happened with the Great Attractor. Each generation of telescopes adds detail. The Norma cluster turned into the Norma Wall. The wall connects to Centaurus Crux and Pavo. The chain extends through Centaurus toward Vela. Beyond all of that sits Shapley. And around Shapley, the cosmic web keeps going, threading deeper into the universe. Our galaxy is not falling toward a marble. It is sliding down a long slope, picking up details with every passing million years. The next surprise about that slope changed how we draw our own home on the cosmic map. For most of the 20th century, our cosmic address ended at the Virgo supercluster. Galaxy, local group, Virgo cluster, Virgo supercluster. Done. Then, in 2014, Brent Tully and a small team published a paper that wiped that address line off the map. Their idea was clever. Instead of grouping galaxies by where they sit, they grouped them by where they are going. They tracked the peculiar velocities of about 8,000 galaxies, then mapped which way each one was flowing. Galaxies that flowed toward the same gravity well belonged to the same supercluster. Galaxies that flowed elsewhere did not. It was the watershed approach again, but applied to the entire local universe. The result redrew everything. The Virgo supercluster, our supposed home, turned out to be a mere lobe of something much larger. The team outlined a new structure 500 million light-years across, containing more than 100,000 galaxies. They named it Laniakea, Hawaiian for immeasurable heaven. Inside Laniakea, 4 major regions feed each other: the Virgo cluster region, the Hydra Centaurus region, the Pavo Indus region, and the Antlia region. All of them, one way or another, lean toward a central low point, the Great Attractor. For the first time, scientists could draw a clean boundary around our home, like outlining a country on a globe. Inside the line, galaxies fall toward our shared center. Outside, they fall toward someone else's. Past the boundary lies the Perseus-Pisces basin, which is its own supercluster. Past another boundary lies the Coma basin. Past another lies the Hercules. Past all of them sits Shapley, the giant. Picture a series of lakes on a tilted plain. Each lake collects water from a specific drainage area. Those drainage areas are basins. Now, imagine the water in these basins is itself slowly flowing toward a deeper master lake further down the slope. That is roughly the picture astronomers found. Local basins all leaning toward larger ones. Larger basins leaning toward Shapley. The discovery of Laniakea felt like a homecoming and an existential shock at the same time. We finally knew our address. We also realized our address was a tiny corner of an even bigger neighborhood we did not control. There is one more strange detail. Laniakea is the same size, basin to basin, as some of its neighbors. But theoretical models predict superclusters that should be 10 times smaller. Real superclusters in our universe are about an order of magnitude larger than what standard cosmology predicts. The structures should not be this big, yet they are. This kind of mismatch is the sort of thing that quietly keeps cosmologists up at night. Either our maps are imprecise, or our model of the universe is missing something important. Recent data has pushed the boundary of these mismatches, not closed them. In late 2024, a follow-up study suggested Laniakea may itself be only a sub-region of an even larger basin centered on Shapley. If that paper holds up, Laniakea is not the top of our cosmic address. Shapley is. The map keeps zooming out. It also keeps suggesting we are a much smaller fish than we thought. Not a galaxy in a supercluster, a galaxy in a province of a province, sliding toward a cosmic capital we will never reach. Speed is hard to feel. Sitting on a plane flying at 600 miles per hour, you barely notice. The trick is the lack of a reference point. Outside the window, the sky looks still. Without a ground to measure against, motion vanishes. Our galaxy has the same problem on a bigger scale. When astronomers first measured the Milky Way's peculiar velocity, the number stunned them. 600 kilometers per second, roughly 1.5 million miles per hour. Direction, the Centaurus and Hydra region. Reference, the cosmic microwave background. Try to picture the speed. In 1 second, we travel about 370 miles. In 1 minute, 22,000 miles. In 1 hour, more than 1.3 million miles. In a single year, our galaxy and everything in it moves over 12 billion miles closer to the Great Attractor. 12 billion miles per year sounds enormous. On a cosmic scale, it is barely a step. The Great Attractor sits about 220 million light-years away. Light travels at about 6 trillion miles per year. So the distance to the Great Attractor in miles is around 1.3 sextillion miles, a 1 followed by 21 zeros. If we keep moving at our current speed, the Milky Way would need over 100 billion years to reach the Great Attractor. The universe itself is only 14 billion years old. The trip is too long. The universe will run out of time before we arrive. Picture a slow walker setting out to cross a continent. They walk steadily. They never stop. After 200 years, they have crossed maybe a single state. After 10,000 years, they may have reached the next region. The continent is bigger than their lifetime. That is our galaxy and the Great Attractor. There is more. Cosmic expansion fights back. Most galaxies in the universe are not pulling closer. They are racing apart, dragged by the expansion of space itself. Our small region, gravitationally bound, holds together. Beyond a certain distance, even gravity loses to expansion. The Great Attractor is just about at the edge of that border. We will never reach it. Not even if we had infinite time. The expansion of space will keep stretching the gap. This is one of the quiet tragedies of cosmic geometry. We are always moving toward the Great Attractor. We will never get there. Like a runner on a treadmill, our speed feels real, but our position never closes the gap. This does not mean the speed is meaningless. The Milky Way, the Andromeda Galaxy, and a few dozen smaller galaxies in our local group are bound together by gravity. They will merge, eventually, into one big galaxy. That part of cosmic destiny is fixed. The rest of the universe is sliding away faster than gravity can pull it back. So the Great Attractor's role in our future is not as a destination, but as a steering wheel. It bends our path. It keeps us from drifting randomly. It anchors our local flow. It gives our galactic neighborhood a center of gravity, even if we will never visit that center. Some astronomers find this comforting. The cosmos is not chaotic. It has structure, geometry, basins, gravity wells. Even if our galaxy gets carried wherever the currents go, the currents are real and stable. We are not rudderless leaves. We are passengers on a slow, preset course. But what powers that course is still being argued over. And the next answer has been sitting under our noses, almost unseen. The Great Attractor is huge. The Norma cluster is real. The Shapley concentration is bigger still. Add up all the visible galaxies in those regions, count their stars, weigh their gas, and tally the numbers. The total still falls short of what the gravity demands. Something else is doing most of the pulling, something we cannot see. That something is dark matter. About 85% of all matter in the universe seems to be made of stuff that does not emit light, does not absorb light, and does not interact with regular atoms in any way we have detected directly. It only reveals itself through gravity. Dark matter is the unseen scaffolding of the cosmos. Without it, galaxies would not have formed. The universe would have stayed a thin soup of hydrogen and helium. With dark matter, gravity could pull regular matter into clumps fast enough to make the structures we see: stars, galaxies, clusters, walls, everything we know. Picture an iceberg. The white tip you see above the water is regular matter. Stars, planets, gas, dust, everything we ever pointed a telescope at. The much larger underwater section is dark matter, 6 times more massive, invisible to our eyes. But its weight controls how the iceberg drifts. In the Great Attractor region, the dark matter is denser than average. Astronomers can measure this indirectly. They watch how galaxies move. They count the visible mass. They subtract one from the other. What is left over is the dark matter contribution. In the Norma and Centaurus area, this contribution is enormous, multiple times larger than the visible mass. This is why early estimates of the Great Attractor gave such big numbers. Astronomers could feel the gravitational pull, but only see a fraction of the source. The rest had to be dark matter, invisibly piled into the same basin. It is also why X-ray surveys initially suggested the Norma cluster was much smaller than expected. The visible cluster had only a fraction of the mass needed. The remaining mass was hidden in the surrounding cosmic web, mostly as dark matter spread along filaments and walls. There is a strange beauty in this. Our galaxy is being dragged across millions of light years by an invisible substance we have never held in a laboratory. Dark matter has not been directly detected on Earth, despite decades of trying. Underground experiments, particle accelerators, sky surveys, nothing. The most current view is that dark matter is some kind of particle, probably very weakly interacting, possibly very heavy or very light. Several theories compete. Each has pros and cons. None has won. What is settled is that the gravity is real. Gravity from regular matter alone cannot explain how galaxies move. Gravity from regular plus dark matter does. The Great Attractor is one of the strongest pieces of evidence for this. The pull is too big to be made of stars alone. Researchers also debate whether dark matter is enough on its own, or whether the laws of gravity themselves need adjusting on cosmic scales. A theory called modified Newtonian dynamics tries to explain the motion of galaxies without dark matter. It fits some local data. It struggles with bigger structures like the Great Attractor and Shapley. Most cosmologists today still favor the dark matter version. It explains too many things at once to abandon. The cosmic microwave background, galaxy rotation curves, cluster collisions, cosmic flow. All of these line up if dark matter exists. They do not all line up if it does not. So the Great Attractor's hand on our galaxy is, in a sense, a dark hand. Long before the Great Attractor's deeper layers were mapped, astronomers needed to prove dark matter even existed. Without that, every claim about giant invisible mass concentrations was speculation. The clearest proof came from a place not too far from the Great Attractor's neighborhood. A pair of colliding galaxy clusters in the southern sky, known by their cataloging name as 1E0657-56, to everyone else, the Bullet Cluster. This system is what happens when two galaxy clusters smash into each other at thousands of kilometers per second. It is one of the most violent events in the local universe. The two clusters did not stop on impact. They passed through each other. The fascinating part is what got separated and what did not. Galaxies inside clusters are mostly empty space. When two clusters collide, the galaxies pass each other like ghosts. They almost never bump. The hot gas between galaxies, however, is dense. When two clouds of gas hit, they slow down, they pile up, they glow bright in X-rays. After the Bullet Cluster's collision, astronomers using the Chandra X-ray Observatory mapped the hot gas. It sat in the middle, where you would expect debris to slow down. Then they mapped the gravitational pull of each cluster by watching how the clusters bent the light of more distant galaxies behind them. This bending, called gravitational lensing, lets you measure mass without needing to see it. The two maps did not match. The hot gas was in the middle. The gravitational mass was on the sides, where the galaxies were, not where the gas was. Most of the mass in each cluster had passed through the collision unaffected. It had not piled up. It had not slowed down. It did not glow in X-rays. It only revealed itself by bending light. The most natural explanation is dark matter. Dark matter does not interact with regular matter through anything but gravity. So when two clusters collide, the dark matter clouds slide through each other without slowing. The visible gas, which interacts strongly, slows down and gets stuck. The bullet cluster shows this in action. It is one of the cleanest observational arguments for dark matter ever made. Theories like modified gravity, which try to explain galactic motion without dark matter, have a much harder time explaining what the bullet cluster looks like. Picture two ghosts and two cars colliding head-on. The cars crumple in the middle. The ghosts pass through and keep going. Photograph the scene. The wreckage is in the middle. The ghosts are on the far sides, drifting away. The same kind of separation is what the bullet cluster shows, only on a cosmic scale. This is important for understanding the Great Attractor because it confirms that invisible gravity sources are real. Dark matter is not a placeholder for ignorance. It is a real, observable component. The Great Attractor's pull, on the order of 10 quadrillion solar masses, is mostly dark matter weight. This also means that when we describe the Great Attractor, we are describing a region where dark matter has clumped most densely. Galaxies are the visible markers of where the clumps are, like flags planted on a hill to show where the high ground is. Galaxies do not make the hill, they just sit on it. The hill itself is dark matter. So when scientists say our galaxy is falling toward the Great Attractor, what they really mean is our galaxy is sliding into a dark matter valley. Stars come along for the ride, gas comes along, planets come along, life comes along. We are all passengers on a ride we cannot see the rails of. Here is something most people never think about. The Great Attractor does not just move galaxies, it bends light and stretches time. Any large mass curves the space around it. This is the heart of Einstein's general relativity, written down in 1915. Mass tells space how to curve. Curved space tells light and matter how to move. Where mass is dense, light bends. Where mass is dense, time runs slower. A planet bends space slightly, a star more so. A black hole drastically, a whole galaxy much more. A cluster of thousands of galaxies, immense. A region containing 100,000 galaxies and tens of thousands of times as much dark matter. Now we are talking serious curvature. The Great Attractor curves space across hundreds of millions of light years. Light from galaxies behind it, when traveling toward us, gets bent. Astronomers have used this to indirectly study the region. A distant galaxy whose image gets stretched or duplicated by an unseen mass is showing us where the gravity sits, even when the source is hidden. This effect is called gravitational lensing. It works like a giant lens in the sky, a really cluttered, irregular lens. But a lens, light passing through the Great Attractor's mass concentration gets focused, distorted, brightened, sometimes even split into multiple images. Surveys have caught examples of this lensing in the Norma region. Faint, distant galaxies appear smeared into arcs. Each arc is a distant galaxy whose light passed through the cluster's gravity field. The shape of the arc tells astronomers exactly how much mass sits in the way. Time also slows down in deep gravity wells. Inside a galaxy cluster, clocks run a little slower than clocks in empty space. The effect is tiny on a galaxy cluster scale. A second is still pretty close to a second, but the difference is real. If you could place a clock at the Great Attractor's center and another in deep intergalactic void, after 1 billion years, the void clock would tick slightly more total time. Picture a heavy ball on a stretched bedsheet. The bedsheet sags. A marble nearby rolls toward the ball. Now, imagine the bedsheet has a clock printed on it. The clock looks normal far from the ball. Near the ball, the clock face is slightly distorted, slightly slower. The Great Attractor is doing this to space all around itself. A photon of light leaving a galaxy near the Great Attractor center has to climb out of the gravity well to reach us. As it climbs, it loses a little energy. We see the light slightly redshifted compared to a galaxy at the same distance but in empty space. This is gravitational redshift, tiny but measurable, and it shows up in cluster studies. For us, riding along with our galaxy, these effects are gentle. The Great Attractor pulls us at 1,000 miles per hour, cumulatively over billions of years. The bending of space we feel is small, but on the right scale, the effect is real and measurable. The Earth's clocks tick a tiny bit slower because of the Sun's gravity. They tick a tiny bit slower than that because of the Milky Way. They tick a tiny bit slower still because of Laniakea. The Great Attractor adds another whisper of delay. We are buried inside layers of gravity wells, each one squeezing time a hair more than the last. If you could leave our galaxy and float in true intergalactic emptiness, your watch would run faster than mine. Not by much, but by something. The structures of the cosmic web are not just ornaments. They warp the fabric we live in. They define how fast time moves for us, compared to elsewhere. The Great Attractor is one of the deeper warps near our address. We live our entire lives in its slight time dent. Zoom out far enough, and the universe stops looking like galaxies in space. It starts looking like foam. Galaxies are not scattered evenly. They cluster along threads. The threads connect into walls. Walls surround empty cells. The whole structure looks like the interior of a sponge or the foam in a cappuccino. Astronomers call this the cosmic web. The web has several main features. Filaments are long threads, often containing chains of galaxies linked by hot gas. Walls are flat sheets, like the normal wall. Nodes are dense knots where filaments meet, often forming galaxy clusters. Voids are the huge empty spaces in between, sometimes hundreds of millions of light years across, like the dipole repeller's center. Galaxies travel along filaments, like cars on a highway. Gas and dark matter funnel down filaments toward the nodes. Once inside a node, galaxies merge, evolve, and pile up. Over billions of years, more matter flows in, and the nodes grow bigger. Our local part of the cosmic web is dense and busy. Laniakea sits at the intersection of several filaments. Beyond Laniakea, more filaments stretch toward Shapley. Beyond Shapley, the web continues. Astronomers can map this structure out to billions of light years using galaxy redshift surveys. Picture a city seen from a satellite at night. You see roads first, then bigger roads, then highways, then cities at the highway intersections. Outside the highways, the country goes dark. The cosmic web looks like that, at the largest scale, except the highways are filaments and the cities are galaxy clusters. The Great Attractor is one of the most prominent local nodes. It sits at the crossing of several filaments. The normal wall is one nearby wall. Shapley is a much bigger node further along. Tracing the lines of the web in our region is like watching water flow downhill. Every drop ends up somewhere. The cosmic web took billions of years to form. In the early universe, just after the Big Bang, matter was nearly evenly spread. Tiny variations in density, on the order of 1 part in 100,000, gave gravity something to grab. Slightly denser regions pulled in more matter. They got denser. The denser they got, the more they pulled. Less dense regions emptied out, growing into voids. This process is called gravitational instability. It is the same physics that drives water to drain into a sink. Once a basin starts forming, it grows. Once a void starts emptying, it empties faster. The web is the result of 14 billion years of this drain and grow process. Computer simulations now reproduce the cosmic web with incredible fidelity. Run the early universe forward in a computer with the right physics and the right amount of dark matter, and out comes a foamy structure that looks very much like the real one. The simulations even predict structures like the Great Attractor and Shapley in the right positions at roughly the right sizes. But there is one stubborn mismatch. As mentioned before, real superclusters in our universe are about 10 times bigger than the simulations expect. Standard cosmological models predict smaller basins. The fact that Laniakea, the Great Attractor Basin, is so huge is a quiet challenge to those models. This is where the cosmic web meets cosmology's open questions. We have a beautiful framework that gets 99% of the picture right. The remaining 1% involves things like the Great Attractor's exact size, dark flow, and the dipole repeller. Each of these corners is where new physics might be hiding. The web is real. The web is mappable. The web is doing things our equations almost predict, but not quite. For decades, astronomers thought the Great Attractor and Shapley were the only big structures hiding behind the Zone of Avoidance. Then, in 2016, a survey using the South African Large Telescope and the Anglo-Australian Telescope spotted something else. Something nobody had mapped before. It sat about 800 million light-years from Earth in the constellation Vela, a massive concentration of galaxies, sprawling across a region 30 by 20 by 10 degrees on the sky. Hundreds of galaxies confirmed in just a small slice of the area. Models suggest the full structure could rival or even exceed Shapley in mass. Astronomers named it the Vela supercluster. The discovery was a shock. By 2016, the cosmic neighborhood was supposed to be well mapped out to 1 billion light-years. Surveys had been combing the sky for decades, yet a structure that big had managed to hide, almost entirely, behind the dust of our own galaxy. The reason was geometry. Vela sits in a particularly nasty patch of the Zone of Avoidance, where the Milky Way's plane is densest. Optical telescopes had no chance. Earlier infrared surveys had picked up hints of something there, but the data was too sparse. Only when astronomers combined deep galaxy surveys with redshift measurements did the structure suddenly emerge. Picture a city skyline obscured by smog. From far away, you can make out a few tall buildings poking through, but you have no idea whether you are seeing a small town or a megacity. Then a wind clears the smog for an hour, and you realize there is an entire downtown stretching for miles. That was the Vela discovery. What makes Vela important for the Great Attractor story is its location. Vela sits beyond Shapley, slightly off to one side, in a direction that overlaps with the broader cosmic flow our galaxy is following. If Vela is as massive as some estimates suggest, it adds another tug to our peculiar velocity. The total cosmic gravitational pull on the Milky Way may not stop at Shapley. It may extend out to Vela and beyond. The current best estimate is that Vela contains the equivalent of a small ocean of galaxy clusters. Multiple rich clusters appear to be embedded in the structure, connected by filaments. The total mass might be in the hundreds of thousands of trillions of solar masses range, big enough to influence the motion of the entire local universe. Vela also raises a deeper question. If a supercluster this big could hide for so long behind the Zone of Avoidance, how many other giants might still be undetected? Every patch of sky we cannot see could contain another monster. Astronomers are now using new instruments specifically designed to peer through the cosmic dust. Radio telescopes like Meerkat and the upcoming Square Kilometre Array, infrared satellites, X-ray observatories. Each of these can look through different parts of the obscured zone. With every new survey, the Zone of Avoidance shrinks a little. There may still be hidden walls and clusters waiting to be found. The Great Attractor was the first big surprise. Vela was the second. There is no good reason to think the surprises have ended. This also reframes the Great Attractor. It is not the central feature of our cosmic neighborhood. It is one node among several giant nodes, each pulling in its own direction. We are surrounded by gravitational neighbors, and one of those neighbors does the opposite of pulling. It pushes. Before any galaxy survey caught the great attractor in motion, an entirely different kind of light gave the first hint that something was off. The cosmic microwave background, the leftover glow from the Big Bang, this faint radiation fills all of space. It is the oldest light in the universe, released about 380,000 years after the Big Bang, when the cosmos finally cooled enough for hydrogen atoms to form. Before that moment, the universe was a dense, hot soup of charged particles. Light could not travel through it. It bounced and scattered like sunlight in fog. Once neutral atoms formed, the fog cleared. Light streamed out. That ancient flash has been traveling ever since, gradually stretching with the expansion of space until it now reaches us as a microwave glow with a temperature of about 2.7 degrees above absolute zero. The microwave background is famously uniform. Look in any direction, and the temperature is the same to about 1 part in 100,000. The early universe was incredibly smooth, but there is one larger pattern. One side of the sky is slightly warmer, the opposite side is slightly cooler. The size of this difference is about 0.003 of a degree. Tiny, but real, and consistent across every measurement made. This warmer-cooler split is called the dipole, and it has nothing to do with the Big Bang. It is caused by us. When you move toward a source of light, the light gets compressed. Its waves bunch up, higher frequency, slightly hotter color. Move away from the same source, and the light stretches out. Lower frequency, slightly cooler color. The microwave background is a wall of light all around us. As we move through it, one side blue shifts and one side red shifts. The hot pole of the dipole points roughly toward the constellations Centaurus and Hydra. The cold pole points the opposite way. The size of the temperature difference tells us our speed, about 630 kilometers per second relative to the average of all matter in the visible universe. This was one of the first hints, in the 1970s, that the local group of galaxies was moving in a peculiar way, not just expanding outward with the universe, moving in a specific direction toward something. That something turned out to be the Great Attractor, and beyond it, Shapley. Picture standing in a misty rainstorm. The drops are falling straight down. If you stand still, you get evenly soaked. Now walk forward. The drops on your face hit harder. The drops on your back are gentler. The cosmic microwave background dipole is the same effect, but the rain is light from the dawn of time, and you are flying through it at 1.5 million miles per hour. The dipole has been measured by every microwave background satellite ever launched. COBE in 1990, WMAP in 2001, Planck in 2013. Each gave more precise numbers, all consistent. We are flying in the same direction, at roughly the same speed, that the original Seven Samurai survey detected from galaxy motion. This is one of the strongest pieces of evidence that the Great Attractor pull is real. Two completely different kinds of measurement, using completely different physics, both point to the same thing. Galaxy redshifts pointed to the attractor. Microwave background dipole pointed to the same direction. They agree. That is how science gets confident. There is one final wrinkle. Recent studies have started to suggest the dipole measured from very distant quasars and galaxies might be slightly different from the dipole measured in the microwave background. If that small mismatch holds up, it could mean cosmic flow is even messier than we thought. That mystery is still being investigated. The Great Attractor sits right at the heart of it. There is one more strange feature in the cosmic microwave background, and it might be related to the Great Attractor's larger story. In 2004, while studying maps of the microwave background, astronomers noticed an unusually cold patch of sky in the constellation Eridanus. The temperature there was significantly lower than expected, not by much, but enough that random noise could not easily explain it. They called it the cold spot. The cold spot is about 2 billion light-years across, as it appears on the sky. To produce it, something would have to be cooling that part of the early universe by an extra fraction of a degree. A few possible explanations have been proposed. The leading theory is that the cold spot is the imprint of an enormous void, a huge underdense region of space sitting between us and the early universe. As microwave light from the Big Bang passed through the void on its way to us, it had to climb out of a slight gravitational well at the far side of the void. That climb cost the light a tiny bit of energy. The light arrived at Earth a hair colder than light coming from regions without a void in the way. If true, the void responsible for the cold spot would be one of the largest empty regions ever detected, several 100 million light-years across, possibly a billion, with far fewer galaxies inside it than expected. This is reminiscent of the dipole repeller. Both involve enormous voids. Both involve subtle but measurable effects on cosmic flows or background radiation. Both challenge the idea that the universe is smooth on the largest scales. Some researchers have suggested the cold spot and the dipole repeller might even be parts of the same larger structure. Recent dynamical analyses of cosmic flow have started linking what used to be considered separate features into a single connected pattern. A giant repeller cold spot complex stretching across a huge fraction of our local universe. Picture standing on a beach and watching waves come in from far away. Most waves arrive normally, but every so often, a wave seems to pause, dragged back by an invisible undertow. The cold spot and the dipole repeller are the cosmic version of that undertow. They are slowing certain regions, bending the flow, leaving fingerprints on the oldest light. The great attractor sits in the middle of all this, pulled forward by gravity from Shapley and Vela, pushed from behind by the dipole repeller and possibly the cold spot region, surrounded by a cosmic landscape of attractors and repellers, all influencing the trajectory of every galaxy in the area. This is the new picture of cosmic flow. It is not just our galaxy falling toward one big mass. It is our galaxy navigating a maze of pulls and pushes, with multiple sources, each contributing a fraction of the total motion. There are still strong skeptics. Some studies in 2024 have argued that the cold spot can be explained by random statistical fluctuations alone. No giant void needed. The argument is open. But if the cold spot really is a void's imprint, and if the dipole repeller is part of the same structure, our universe contains underdense regions far larger than predicted by the standard model. Just like superclusters in our area are larger than predicted, the biggest structures, on both ends, are turning out to be more extreme than the models say they should be. This is one of the hottest unsolved puzzles in modern cosmology, and the great attractor is the closest visible piece of it. For most of this story, the great attractor has been presented as a normal feature of the universe, a big concentration of mass, a combination of clusters, walls, gas, and dark matter. Standard physics, just on an unusual scale. But over the years, fringe and serious scientific suggestions have wondered whether the explanation is incomplete, whether the cause of the cosmic flow we observe might involve something we have not yet imagined. One such idea is that the great attractor's pull, especially the dark flow extension first proposed by Kashlinsky, might be a sign of structures beyond the observable universe. The observable universe is finite. It is the bubble of space whose light has had time to reach us in the 14 billion years since the Big Bang. Anything beyond that bubble is unreachable. We will never see the light from those regions. It has not had time to arrive. Standard cosmology assumes that beyond the observable bubble, the universe continues uniformly, with similar densities and similar physics, just more of the same. If true, the gravitational pulls from beyond the bubble should cancel out on average. Equal pull from all directions equals zero net pull. But what if they do not cancel? What if there is some lopsided structure beyond the observable horizon, one giant region of mass on one side, pulling everything inside our bubble toward it? This is the wildest version of the dark flow hypothesis. Some researchers propose that during the very first instant after the Big Bang, A process called inflation could have left massive structures stretched far beyond what we can see today. If those structures are uneven, they could exert a slight gravitational tug on the part of the universe we live in. Pictures of the implications are intense. Imagine standing in a dark room. You feel a faint draft on your cheek. You know there must be a window somewhere, even though you cannot see it. You will never reach the window because the room is infinite, but the breeze is real. Dark flow, in this version, is the breeze from a window we will never see. Most cosmologists are skeptical of this idea, but not dismissive. The data is too sparse to confirm. The follow-up studies using Planck satellite measurements suggest the dark flow signal is much weaker than first reported. But it has not been completely ruled out either. Other speculative ideas have been proposed. One is that the great attractor's mass might include exotic forms of matter beyond ordinary dark matter, maybe primordial black holes formed in the first second of the universe, clustering together in dense regions, maybe weakly interacting bosons that behave differently from particles, maybe even modifications to the laws of gravity itself, where on certain scales, gravity behaves slightly differently than Einstein predicted. None of these have been proven. Most are not even widely held theories. They are footnotes to the main story. The main story remains that the Great Attractor is a mostly mundane combination of regular galaxies, gas, and dark matter, sitting at a node in the cosmic web. But the very existence of these speculative ideas tells us something. The Great Attractor sits at a frontier. It is the closest thing to us that resembles the largest scale structures of the universe. Anything weird going on at cosmic scale would show up here first. So far, nothing definitively weird has been found, but we are still looking. The Zone of Avoidance was the single biggest obstacle to studying the Great Attractor. Solving it required clever telescopes, lots of patience, and a willingness to trust unusual kinds of light. Optical telescopes were the first try. Surveys like the early sky scans gave up on the zone after realizing the dust extinction was too severe. Some attempts in the 1970s and 80s found a few galaxies poking through thinner patches, but most of the region was a blank. The first real breakthrough came from radio telescopes. Radio waves travel through cosmic dust without much absorption. The Parkes telescope in Australia ran a multi-decade survey of the zone, looking specifically for the radio signature of neutral hydrogen gas in galaxies. Hydrogen emits a faint signal at a wavelength of 21 centimeters. Galaxies full of cool gas show up as bright spots in this radio map. The Parkes survey found thousands of new galaxies in the zone. Many of them were grouped into clusters and walls that nobody had catalogued. Crucially, several of these clusters lined up with the predicted location of the Great Attractor. The radio data was the first direct evidence that real, massive structures lay behind the dust. Next came infrared telescopes. Infrared light, unlike visible light, passes through dust more easily. Surveys like the 2-micron all-sky survey, completed in 2001, mapped the infrared sky completely, including the Zone of Avoidance. Galaxies that had been invisible in optical light became clearly visible in infrared. The infrared surveys revealed even more structure. The Norma cluster's full extent, the connections between clusters, the shape of the Norma wall. X-ray telescopes added another layer. Hot gas in galaxy clusters emits X-rays. The CIZA project, mentioned earlier, used X-rays to find clusters that had been hidden in the zone. CIZA found dozens of new clusters. Some were small, some were significant. One, CIZA J 1324-7, turned out to be a major component of the Norma wall. Combine radio, infrared, optical, and X-ray data, and the once invisible Zone of Avoidance becomes visible. Each kind of light shows different parts. Layered together, the picture becomes clear. Picture trying to describe a forest at night. With your naked eye, you see almost nothing. With a flashlight, you see tree trunks. With a thermal camera, you see warm bodies of animals. With night vision goggles, You see leaves and shapes. No single tool tells the whole story. Combine them, and the forest comes alive. Modern surveys are pushing further. The square-kilometre array, currently being built across South Africa and Australia, will be the most sensitive radio telescope ever made. It will map hydrogen in the zone of avoidance with extraordinary detail. The Vera Rubin Observatory, which started science operations in 2025, will scan the southern sky every few nights, building deep optical maps. The James Webb Space Telescope can probe through thick dust in infrared, finding the most obscured galaxies. Each new instrument adds resolution. With each round of data, the Great Attractor region looks less mysterious and more like a normal but very crowded part of the cosmic web. But there is still mystery. The exact contributions of each component, the dark matter distribution, the connections between Norma and Vela and Shapley, all of these are still being mapped in detail. The zone of avoidance is no longer a blank patch. It is a part of the cosmic map, slowly coming into focus. The Great Attractor is the most studied feature inside it, and every new telescope brings sharper answers. Before we knew about the Great Attractor, before astronomers could even imagine that galaxies could move in coordinated streams, the picture of the universe was much simpler, just an expanding sea of points, all flying outward from a long-ago explosion. The first hint that this picture was incomplete came in 1929. Edwin Hubble, working at the Mount Wilson Observatory, found that distant galaxies were redshifted in proportion to their distance. The further away, the faster they were receding. This was the first solid evidence for the expansion of the universe. For decades after that, cosmologists assumed the expansion was uniform. Galaxies just moved apart. Local clumps formed, but the overall picture was smooth. In the 1970s, a few astronomers started noticing that some nearby galaxies seemed to move slightly differently than the simple model predicted. Vera Rubin and Kent Ford, while studying galaxy rotation, noticed that the Andromeda galaxy was moving toward us, not away. This made sense because Andromeda is gravitationally bound to our local group, but it raised the question of whether other coordinated motions might exist. Then came the Seven Samurai in the early 1980s. Their work on elliptical galaxies revealed the first evidence of streaming motion. Not just our local group, but a much larger region was being pulled together. Around the same time, Vera Rubin and others were finding strong evidence for dark matter from galaxy rotation curves. The two ideas connected. Dark matter could explain how the Great Attractor pulled so much mass. The 1990s brought big galaxy surveys, the 2-micron all-sky survey, the early Sloan digital sky survey. These collected redshifts for hundreds of thousands of galaxies, allowing astronomers to map the cosmic web in 3 dimensions. The web turned out to be real, complex, and full of structures like the Great Attractor. The 2000s brought even bigger surveys. The COBE, WMAP, and Planck satellites mapped the cosmic microwave background, confirmed the Big Bang model, measured the dipole, provided precise constraints on dark matter and dark energy. The whole picture started to come together. In 2005, the CESA X-ray survey found new clusters in the zone of avoidance. In 2008, Kashlinsky proposed dark flow. In 2014, Brent Tully and his team defined Laniakea. In 2016, the Vela supercluster was discovered. In 2017, the dipole repeller was identified. Each step added detail. The Great Attractor went from being a single unknown feature to being one node in a complex landscape of attractors, repellers, walls, voids, and filaments. The picture got richer. The picture got stranger. In 2023, a new analysis using Cosmic Flows 4 data confirmed Laniakea, but suggested it might be only a sub-region of an even larger basin centered on Shapley. This is still being debated. Picture watching a city grow over decades, from a single hut to a few houses, to a small town, to a city, to a sprawling metropolis. Each year adds buildings, streets, neighborhoods. That is how our knowledge of the Great Attractor has grown, from a single anomaly to a whole structure of structures. We are now in an era where almost every month, a new paper refines the picture. New data from Vera Rubin Observatory, new analyses from DESI, new infrared maps. The Great Attractor is the most studied node in the cosmic web. We know it well, but we still do not know everything. This is the nature of cosmology. Every answer creates new questions. Every map reveals new edges to explore. What happens to the Milky Way over the next billion years, the next 10 billion, the next 100 billion? A lot of it depends on the Great Attractor and its larger context. In about 4 to 5 billion years, the Milky Way is expected to collide with the Andromeda Galaxy. This collision will not destroy stars. The space between stars is vast, but the two galaxies will gravitationally tear at each other, fling stars into long tidal tails, and eventually merge into a single elliptical galaxy. Astronomers sometimes call the future merged object Milkdromeda. After that, our merged galaxy will continue along the cosmic flow, still pulled toward the Great Attractor and Shapley. The local group itself, including smaller satellite galaxies, will all eventually merge into Milkdromeda or be flung out into space. Beyond 5 billion years, the picture changes. The expansion of the universe is accelerating. Driven by dark energy, the spaces between gravitationally bound structures are growing faster every year. After a few tens of billions of years, the cosmic flow that currently pulls us toward the Great Attractor will start to lose its battle with expansion. The Great Attractor will still be pulling, but the space between us and it will be expanding faster than the pull can close. We will keep moving toward it, in some sense, but we will never get any closer. After 100 billion years, distant galaxies will redshift out of view. Even Shapley, even Vela, even the Great Attractor itself will recede into invisibility from any observer in our merged galaxy. The universe will feel like it is empty, except for the local group itself. Eventually, after tens of trillions of years, even the merged Milkdromeda will be the only visible structure. Stars will burn out one by one. Black holes will dominate. The cosmic web will dissolve from view. Picture sailing on a vast ocean. A current pulls your ship slowly toward a distant island. For thousands of years, you can see the island getting closer. Then the wind picks up against you. The current keeps pulling, but the wind is stronger. The island stops getting closer, then it starts getting farther. Eventually, it disappears below the horizon. You are still being pulled, but the pull is no longer enough. That is the future of the Milky Way in the cosmic flow. Some cosmologists find this lonely picture bleak. Others find it strangely beautiful. The structures we are part of are real, but they have a finite lifetime in our visible existence. Our galaxy has its current of attraction. Then expansion takes over. Then the visible universe shrinks to almost nothing. There is one nuance. The merger of the local group will produce a stable elliptical galaxy that could survive for trillions of years. The stars inside it will continue to burn, fade, and form new generations from cosmic gas. Life, if it exists elsewhere, could persist for a long time. But the cosmic flow we are currently riding will not keep flowing forever. The Great Attractor's pull will weaken with cosmic time, or rather, our ability to feel its pull will weaken as space stretches between us. The universe is not static. The forces shaping our motion are themselves changing. The Great Attractor was a dominant feature for the first half of cosmic history. In the second half, it slowly fades from relevance to any observer near us. We are riding a current that has a beginning, a middle, and an end. We are roughly in the middle right now. There are still plenty of billions of years left for the pull to keep tugging. But the future is not infinite acceleration toward the attractor. It is a gradual disconnection. Cosmic loneliness is the price of cosmic time. Throughout this story, certain numbers keep shifting. Distance to the Great Attractor, sometimes given as 220 million light-years, sometimes 250 million, mass estimates ranging from 10,000 trillion solar masses to 10 quadrillion. Velocity of our galaxy, sometimes 600 kilometers per second, sometimes 630. This is not sloppiness. This is the nature of measuring things at cosmic scale. Each measurement depends on assumptions. How do you define the boundary of the Great Attractor? Is it the Norma cluster alone? The cluster plus the surrounding wall? The whole Laniakea basin? Different definitions give different masses. How do you measure the distance? Using redshift, you have to assume a value of the Hubble constant, the rate of universal expansion. Different methods give different values. Using distance ladders like exploding stars and pulsing stars, you have to calibrate each rung. Tiny errors compound. How do you measure peculiar velocity? You compare redshift to distance. But your distances have uncertainty, so your velocities have uncertainty. Statistical analyses across thousands of galaxies improve the picture, but not perfectly. This is why the Great Attractor's properties are reported with ranges. The mass estimate of about 10 quadrillion solar masses has a wide uncertainty. The exact location is fuzzy. The contribution to our motion versus Shapley's contribution is debated. The estimates have shifted as new data arrives. Picture trying to weigh a herd of elephants from a helicopter. You can see them. You know roughly where they are. You count them, but you cannot put them on a scale. You estimate their mass from how the ground deforms under their feet, viewed from above. That is roughly what astronomers do with the Great Attractor. Indirect, statistical, rough. The bigger insight is that all the measurements agree on the key facts. There is a major attractor in the Centaurus and Hydra direction. It is several 100 million light-years away. It contains a lot of mass. Our galaxy is moving toward it at a few 100 kilometers per second. That much is settled. The disagreements are about the precise details. Is the dominant pull from the Norma wall or from Shapley? How much do voids like the dipole repeller contribute? How does Vela factor in? These are real debates with real data. The funny thing is, this kind of fuzziness applies to almost everything in cosmology. The Hubble constant has been controversial for years. Different methods give slightly different values. The dark energy equation has uncertainties. The dark matter distribution has uncertainties. The age of the universe has uncertainties, though small ones. Despite all this, the overall picture has held up remarkably well. Big Bang, expansion, dark matter, dark energy, cosmic web. The skeleton of cosmology is robust. The flesh on the bones, the precise numbers, gets refined every year. The Great Attractor sits in this regime. The picture is solid. The exact numbers are still being polished. For some people, the lack of crisp numbers is frustrating. For most cosmologists, it is exciting. Every disagreement is a hint. Every tension between datasets points to where new physics might hide. Every refinement of mass or distance estimates is a step closer to understanding the true structure of our universe. Imagine, just for fun, that humanity could send a probe to the Great Attractor. What would the journey be like? First, the distance. About 220 million light-years. At the speed of light, the trip would take 220 million years. At 10% of the speed of light, 2.2 billion years. At 1% of the speed of light, 22 billion years. There is no realistic technology, even theoretical, that could make this trip in any reasonable amount of time. Second, the destination. The Great Attractor is not a single point you can land on. It is a region of space, several 100 million light-years wide, containing many clusters, walls, and filaments. There is no center. Exactly. There is no surface. There is just a deeper gravitational well as you go in. Third, the experience. As you approach the region, you would notice the density of galaxies increasing. More galaxy clusters in your view, more gas and dust, more background light. The microwave background dipole would shift. Time would slow down by a tiny amount. Picture flying a spacecraft toward a city at night. Far out, you see a few scattered streetlights. As you get closer, the lights cluster. Roads appear, then highways. then buildings. The city itself is bright, busy, complex. You can never reach the absolute center. The center is just where the buildings are densest. The Great Attractor would feel similar. You would see the cosmic web getting denser. You would pass through filaments. You would orbit through walls. You would visit individual clusters, but there would be no signpost saying you have arrived. If you could somehow visit the Norma cluster directly, you would find something extraordinary. Hundreds of galaxies packed into a region only 10 million light-years across. Inside, the most active galaxies emit massive radio jets. Hot gas at temperatures of millions of degrees fills the space between galaxies. Galaxies move at thousands of kilometers per second relative to each other. The most violent regions, near the cluster cores, are dangerous. Galaxy collisions are common over long timescales. Stars get flung. Tidal forces strip outer parts of galaxies. New stars form from compressed gas and then quickly get scattered. If you visited Shapley, the picture would be similar but bigger. More galaxies, more gas, more gravity. A truly epic cosmic city. What you would notice, traveling between these regions, is that they are not isolated. They are connected. Long filaments of galaxies stretch between them, like cosmic highways. Gas and dark matter flow along these filaments. Galaxies migrate. Mergers happen. You are inside the cosmic web, looking around. The Great Attractor is the densest hub in our local part of it. In real terms, no probe will ever go there. Not in any human timescale. Not in any galactic timescale. But the picture of going there is useful. It reminds us that the Great Attractor is real, made of galaxies, made of stars, possibly made of life forms we will never meet. Somewhere in the Norma cluster, there might be planets where intelligent beings are looking up at their own night sky, wondering what is pulling their galaxy towards some distant point. Their answer, if they have figured it out, would include their version of Shapley, of Vela, of the dipole repeller. They would have their own cosmic address. We are all neighbors in the same cosmic web, just very far apart. Here is something most coverage of the Great Attractor leaves out. There are still scientists who think the original Great Attractor concept may have been overstated. The original story said that a single huge mass concentration, 220 million light-years away, was pulling our galaxy. The Norma cluster was supposed to be at its heart. The mass was supposed to be on the order of 10 quadrillion solar masses. Newer analyses have softened this picture. The Norma cluster is real, but its mass is closer to the size of a typical rich galaxy cluster. Not a continent of galaxies, just a normal big cluster. The cosmic web around it is dense but not anomalously so. The remaining gravitational pull, the part that the Norma cluster cannot account for, comes mostly from Shapley. Shapley is twice as far away, but much more massive. So the original Great Attractor is now better understood as a collaboration between the Norma cluster and Shapley, with Norma as the closer foreground object and Shapley as the larger background mass. In this view, there is no single mysterious gravity well, just a chain of normal cosmic structures, each contributing its share of pull. The dramatic original story of a hidden anomaly turns out to be more like a normal feature of the cosmic web seen through dust. Some astronomers go further. They argue that the original mass estimate of the Great Attractor was inflated by the limits of early data. Once you correct for those limits, the pull is just consistent with standard cosmology. No new physics needed, no mysterious unknown source. The Cosmic Flows 4 dataset in 2023 found a small tension with standard cosmology, on the order of 0.1%. Not zero, but small. This could mean either underestimated uncertainties or new physics. Most cosmologists lean toward the former. If the conservative view is right, the Great Attractor is mundane, a normal node in the cosmic web. The fascination it once held was due to incomplete data, not actual exotic physics. But this view is not universal. Other astronomers point to remaining puzzles. The size of Laniakea is anomalous compared to predictions. The dark flow signal, while weakened, has not been completely ruled out. The dipole repeller is bigger than expected. These hints, taken together, suggest something beyond standard cosmology might still be hiding. Picture two scientific camps. One camp says everything is fine, no new physics needed. The data fits standard cosmology with small errors. The other camp says the cumulative tensions suggest something is missing from our model, and the Great Attractor region is where the cracks first showed. Both camps use the same data. Both have reasonable arguments. The disagreement is about how to weigh tensions versus errors. Different scientists weigh them differently. This is healthy. Science advances by debate. The Great Attractor remains a frontier object in the sense that it sits exactly where the standard model is most stretched. Whether the stretching matters or not is still being argued. For us, watching from the outside, the takeaway is that the universe is not a finished story. The Great Attractor is not a settled fact. It is a region of cosmic interest where the data is most contentious, where surprises might still wait. The Great Attractor does not exist alone. It is part of a much larger study of cosmic flows, and cosmic flows are now one of the main testing grounds for fundamental physics. The basic idea is simple. The motion of galaxies, on top of cosmic expansion, depends on the distribution of matter. If our model of matter is right, the predicted flow should match the observed flow. If they disagree, something is missing from our model. The standard model is called lambda CDM. Lambda stands for the cosmological constant, representing dark energy. CDM stands for cold, dark matter. This model predicts how galaxies should cluster, how walls should form, how voids should evolve. It has been remarkably successful at predicting the cosmic microwave background, the cosmic web, and the rate of expansion. But the model has tensions. Recent measurements of the Hubble constant from the cosmic microwave background versus from local distance ladders give slightly different values. This is called the Hubble tension, and it is one of the hottest debates in cosmology. Cosmic flows are another testing ground. If the standard model is right, the flows in our region should be consistent with the matter distribution we observe. Surveys like Cosmic Flows 4 have measured these flows in detail. Most of the data fits the standard model, but there are small tensions, especially in the Great Attractor region. The dark flow signal, even if weakened, is one such tension. The size of the dipole repeller is another. The size of Laniakea is another. Some theoretical physicists think these tensions point to new physics. Maybe dark matter is more complex than a simple cold particle. Maybe gravity behaves slightly differently on the larger scales. Maybe the universe's geometry has a small curvature we have not yet detected. Each of these would be revolutionary. But none of them is required by the data yet. The tensions are real but small. The Great Attractor region is where these tensions are most concentrated, so studying it carefully matters. If new physics is hiding in cosmic flows, this is where it would show up first. Picture detectives investigating a crime scene. Most of the evidence fits a simple explanation, but there are a few small inconsistencies, a footprint that does not match, a timestamp that is off by minutes, a witness who says something slightly different. Detectives have to decide whether these inconsistencies are noise or whether they point to a different story. Cosmologists are doing the same with the Great Attractor. Most evidence fits standard cosmology. A few inconsistencies remain. Are they noise or are they pointing to something deeper? The next decade should give us better answers. New surveys are coming. The Vera Rubin Observatory will improve galaxy distance measurements significantly. DESI is mapping millions of galaxies. The Euclid satellite, launched in 2023, is mapping the cosmic web in detail. The James Webb Space Telescope is probing the deep universe. By the early 2030s, we should have much better measurements of cosmic flows. Either the tensions will resolve, or they will sharpen. Either way, the Great Attractor will play a central role in the answer. This is why the topic still matters. Not because the Great Attractor is exotic, but because it is at the frontier of what we can measure. And the frontier is where physics is most likely to reveal new layers. Let us pause the physics for a moment. Let us think about what the Great Attractor means in human terms. For most of human history, we believed Earth was the center of everything. Then we learned the Sun was the center, then the galaxy, then the cluster, then the supercluster. Each step humbled us. Each step made our place in the universe smaller. The Great Attractor is the latest in this series. It tells us that even our supercluster is not central. We are sliding, in a slow but unstoppable way, towards something larger. This is a strange feeling. We live our entire lives feeling settled in place. Earth feels solid under our feet. The night sky feels eternal. Stars feel fixed. Yet on cosmic scales, none of this is true. Earth is racing around the Sunday. The Sun is racing around the Milky Way. The Milky Way is racing toward the Great Attractor. We are all moving, all the time, in directions we did not choose. The question is what to do with this information. Some people find it terrifying. Others find it humbling. Others find it freeing. Carl Sagan famously called Earth a pale blue dot, a tiny speck in the vast cosmic ocean. The Great Attractor extends this picture. We are not just a dot, we are a moving dot. We are not just small, we are caught in currents we do not understand, yet we know about it. That is the remarkable thing. A species that evolved on a small planet around an ordinary star has figured out, through telescopes and physics and patient measurement, that it is being pulled toward a hidden mass 200 million light-years away. We have mapped the pull, named the source, measured the speed, argued about the meaning, and we have done all this in less than 100 years. The Great Attractor is a story of human curiosity as much as cosmic structure. Every step in the story involved astronomers refusing to accept incomplete data, refusing to stop looking through the dust, refusing to take old maps as final. The seven samurai measured galaxies one by one. The Parkes telescope scanned the radio sky for years. Cosmic Flows compiled tens of thousands of distance measurements. Each step took patience. Each step took technology. Each step took willingness to be wrong and try again. Picture watching a small child learn to walk. They fall, they get up, they fall again, they get up. Eventually, they walk, then they run, then they explore. The history of mapping the Great Attractor is the history of our species learning to walk in the cosmos. Each generation of telescopes is a new step. We are still falling sometimes. We are still arguing. We are still finding new mysteries. But we are also still moving forward, slowly, gathering more of the picture. The Great Attractor will not be the last thing we discover at this scale. Beyond it, beyond Shapley, beyond Vela, more structures wait. The universe is too big and too rich for any one survey to finish the map. There will always be a next mystery. For us, sitting on Earth, the Great Attractor is a reminder. The universe is not finished. We are not at the center. We are not the most important thing, but we are paying attention, and paying attention on cosmic scales is its own kind of greatness. Step back to the basic question. Why did it take so long to find the Great Attractor? The answer, as we have seen, is the Zone of Avoidance. Our own Milky Way's dust and stars block 1/5 of the sky. The Great Attractor sat behind that dust. So did Vela. So did parts of the Norma Wall. This is a striking fact about our cosmic situation. Our home galaxy, beautiful as it is from outside, is also our biggest obstacle to seeing the larger universe. The dust that makes the Milky Way glow at night is the dust that hides the cosmic neighborhood beyond. There is something poetic about this. Our position inside the galaxy is what gives us the experience of being in it. The same dust that makes the night sky look magical is what blocks our view of bigger structures. To see the Great Attractor clearly, we would need to leave our galaxy, not in person, but through telescopes that see through dust. It took decades to develop those telescopes. Radio, infrared, X-ray. Each one had to be built, calibrated, deployed. Each one had to scan years of sky to gather enough data. The Great Attractor was hiding in plain sight, but we needed the right kind of eyes to see it. This is a useful lesson for science generally. When something seems missing from our model, sometimes the missing piece is not really missing, it is just unobserved. The Great Attractor was always there, exerting its pull. We just could not see what was doing the pulling because the dust was in the way. Other parts of the cosmos may have similar hidden features. Gravitational waves from distant black hole mergers were predicted decades before we could detect them. Dark matter was inferred from galaxy rotation before any direct detection effort. The cosmic microwave background was predicted as a residual glow before the first satellite measured it. Each of these was hiding in plain sight, waiting for the right instrument. The Great Attractor was the same. Picture a museum hall. 1,000 paintings hang on the walls. Each painting is illuminated by a small lamp. Most of the paintings are clearly visible, but one painting, the most interesting one, sits in a shadow. The lamps are weaker there. Dust hangs in the air. To see the painting clearly, you have to bring a flashlight, an X-ray imager, an infrared camera. With each new tool, the painting reveals more detail. That is what happened with the Great Attractor. We brought new tools to a poorly lit corner of the cosmic hall. With each tool, the picture became sharper. The zone of avoidance is shrinking, not because our galaxy is moving out of the way, but because our instruments are seeing through it better. The Square Kilometre Array will accelerate this further. New infrared satellites will help. Each new survey peels back another layer of obscurity. Within a few decades, the zone of avoidance may be effectively gone. We will see through it almost as well as we see through any other part of the sky. The Great Attractor will be one of the most thoroughly mapped regions in the universe. Its mass distribution will be known to high precision. Its dark matter will be mapped. Its connections to Shapley and Vela will be charted in detail. Then the Great Attractor will be a fully solved puzzle, a normal but interesting feature of the cosmic web, worth knowing, worth studying, but no longer mysterious. For now, in the year 2026, it is still partly mysterious. We are in the middle of solving it, and that is the most exciting time to be paying attention. Inside the Great Attractor region, things are not peaceful. Galaxy clusters are some of the most violent environments in the universe. The Norma cluster, the central cluster in the Great Attractor, is a hotbed of cosmic activity. When two galaxies inside a cluster pass close to each other, gravity pulls on their outer stars and gas. Tidal tails form. Streams of stars get flung out. Some galaxies merge. Others get stripped of their gas. New stars form in compressed regions. Old stars get swept into the cluster's general background. The hot gas between galaxies, called the intracluster medium, is itself a major player. It heats up to tens of millions of degrees as it falls into the cluster's gravity well. It glows brightly in X-rays. When two clusters collide, like the bullet cluster, the gas piles up and creates spectacular shock fronts. The Norma cluster has been observed in X-rays for decades. Its hot gas glows steadily. Inside, individual galaxies move at thousands of kilometers per second. The whole cluster is a roaring environment, churned by gravity. At the heart of the Norma cluster, the giant elliptical galaxy, ESO 137 to 006, hosts a supermassive black hole at its center. This black hole is feeding. It pulls in gas from its surroundings. Some of that gas falls inward, releasing huge amounts of energy as it heats up. The rest gets blasted out as relativistic jets. The jets are extraordinary. They stretch for millions of light years from the central galaxy. They emit radio waves visible from Earth, even through cosmic dust. They carve channels through the cluster's hot gas, leaving cavities filled with relativistic particles. The cavities glow in radio. The channels glow in X-ray. This is a beautiful and violent ecosystem. Galaxies do not sit still in clusters. They migrate, merge, get torn apart, rebuild. The Norma cluster is a microcosm of cosmic structure formation, happening in real time over billions of years. Picture a busy city block during rush hour, people streaming in different directions, some merging into a building, some leaving, some standing still. The city itself does not move much, but its parts are constantly rearranging. The Norma cluster works the same way. The cluster as a whole is held together by gravity, but the galaxies inside it are constantly shuffling. If our galaxy were to fall into the Norma cluster, eventually we would join this cosmic dance. Of course, we will never get there. The expansion of the universe is too fast. But if we could, the Milky Way would be one more galaxy among hundreds, in a chaotic environment where mergers, tidal disruptions, and starbursts are everyday events on cosmic timescales. For us, watching from outside, the Norma cluster is fascinating to study. It tells us how clusters work, how galaxies evolve in dense environments, how dark matter shapes large structures. Each galaxy in the cluster is a data point. Together, they map the gravitational landscape. The Great Attractor is not just a passive gravity well. It is full of activity. Stars form, galaxies merge, black holes feed. The whole region is a working cosmic factory. This is one of the things astronomers find most wonderful about studying it. The universe is not a still picture. It is a moving system, with structures evolving on every scale. The Great Attractor sits at one of the most active local nodes. Its history, its present, its future are all woven together. We are pulled toward this activity, but we will never reach it. We can only watch from afar, and what a view it is. Now consider a thought experiment. What if Earth could feel the Great Attractor's gravity directly? The answer is, we already do. We just do not feel it as a force. We feel it as motion. Our galaxy is being pulled at 1.5 million miles per hour relative to the cosmic background. Earth rides along with the galaxy. So Earth, you, your house, and your morning coffee are all moving at 1.5 million miles per hour toward the Great Attractor. The reason we do not feel this is the equivalence principle. Free fall is indistinguishable from rest. As long as nothing is opposing the gravitational pull, we just fall. We coast, smooth and silent. We feel like we are sitting still. If the Great Attractor were close, we would feel its tidal forces. The pull on the side of Earth nearest to the attractor would be slightly stronger than the pull on the far side. This difference would stretch us out in one direction, but the Great Attractor is 220 million light-years away. The tidal forces from such a distance are negligibly small. Earth has not been measurably stretched by the Great Attractor's gravity. The Sun and the planets stay in their orbits without disturbance. Closer to home, the Sun has tidal effects that we do feel. The Moon raises tides on Earth's oceans every day. Other planets exert tiny forces. But the cosmic web of attractors is so distant that, on human timescales, we feel nothing. Picture being on a slow conveyor belt at an airport. The belt moves you forward, but you feel like you are sitting still. The walls slide by, but everything on the belt with you is stationary relative to you. We are on the cosmic conveyor belt. Earth, the Sun, the planets, the Milky Way, all moving together at 1.5 million miles per hour. Inside our reference frame, nothing seems to move. The only way to detect the motion is to look at the cosmic microwave background. The dipole pattern in that ancient light tells us we are moving. Without it, we would never know. This is one of the strangest aspects of cosmic motion. We are racing through space, but we cannot feel it. We are being pulled by a hidden mass, but we cannot detect the pull directly. We can only see the consequences, the motion, the dipole, the slight tensions in cosmological models. This invisibility of cosmic motion is humbling. Our subjective experience of being settled in place is an illusion, but it is a useful illusion. We do not need to feel the cosmic flow to live our lives. The universe arranges itself so that local physics works locally. We can ignore the larger picture and still get through our days. But knowing about it changes something. Every time you look up at the night sky, You are looking at stars that are moving with you, at galaxies that are pulling on you, at structures so vast they bend the very fabric of space. You are in motion. The universe is in motion. Nothing is still. Some people find this unsettling. Others find it inspiring. Knowing the truth about our cosmic motion does not change our daily lives, but it changes our sense of place. We are not at a fixed point. We are travelers on a long, slow journey toward a destination we will never reach. The Great Attractor is the largest signpost on this journey. It is not the end of the road. It is just the most prominent feature on the way. We end where the universe begins to fade from our reach. The Great Attractor is not the largest structure in the cosmos. Beyond it lies Shapley. Beyond Shapley, possibly Vela. Beyond Vela, more cosmic web stretching to the edge of the observable universe. Beyond that edge, we cannot see. Anything there is forever invisible to us, no matter how long we wait. The cosmic flow we have traced in this story extends as far as our telescopes can reach, possibly farther. The dark flow signal, if real, suggests influences from beyond the visible horizon. Whether or not that signal is real, we know that gravitational influences from very distant structures contribute to local motion. The Great Attractor is one node in a complex network of pulls and pushes. What lies beyond what we can see? Standard cosmology says more of the same. More cosmic web, more attractors and repellers, more galaxies and voids. The universe is statistically uniform on the largest scales. Wherever you go, the average density should be similar. But standard cosmology might be wrong on this point. Some theories of inflation suggest the early universe stretched in such a way that distant regions could differ from our region. There could be larger structures beyond the horizon that we will never see directly. Their gravitational influence might still reach us, faintly, in cosmic flow patterns. This is the edge of knowing. Beyond this point, we are speculating. The data is too sparse. The signals are too weak. The universe is too large. Picture a sailor in the middle of an unknown ocean. Maps exist for the region nearby. Stories exist about more distant lands. Beyond the stories, only blank parchment. The sailor can speculate about what might lie beyond, but cannot verify it without traveling there. We are in this position. The Great Attractor is in our nearby waters. Shapley and Vela are in the next bay over. Beyond them, the sea stretches further than we can ever sail. But there is a different kind of progress we can make. We can refine our maps of what we can see. We can make our measurements of cosmic flow more precise. We can better understand the contribution of voids, walls, and clusters to local motion. We can resolve the small tensions in our cosmological model. We can learn whether the Great Attractor and Shapley fully explain our motion, or whether something extra is hiding. Each new generation of telescopes brings sharper answers. The Vera Rubin Observatory, the Euclid satellite, the Square Kilometre Array, all are in operation or coming online soon. By 2030, we should have much better measurements. By 2040, perhaps definitive ones. The Great Attractor itself will not change in this time. It will continue to do what it has been doing for billions of years, pulling, attracting, anchoring our supercluster. The expansion of the universe will continue to fight against this pull. The flow will continue to slow over cosmic time, but our understanding of the Great Attractor will sharpen. We will learn whether dark flow is real. We will learn the precise mass distribution. We will learn the contributions from voids and distant superclusters. We will close the small tensions in our model, or we will find that they do not close, and new physics is needed. The story is not over. It is being written in observatories and on supercomputers, in journal papers and at conferences. Every year, the picture gets clearer. For us, watching from Earth, this is an extraordinary time. We are alive during the era when humanity is learning, with real data, what is pulling our galaxy across space. Future generations will know more, but we are the ones who first learned the basics. We are the ones who first named the Great Attractor. We are the ones who first realized that something enormous, something hidden, something that changes the fate of our cosmic neighborhood, was sitting just behind the dust of our galaxy all along. That is something worth knowing. The universe does not owe us understanding, but we have built it anyway. Telescope by telescope, paper by paper, mile by mile of cosmic motion. The great attractor is no longer a mystery without explanation. It is a feature with a story that our species has earned through patience and curiosity, the right to tell.